So far we have seen plumes forming due to continuous release of buoyant fluid. And now we are going to see what happens if a fixed volume of buoyant fluid is released rather than continuous injection. So you see few images here, and the first image that you see, this is something we have been seeing quite frequently, and this is with continuous injection. So when you continuously inject some buoyant fluid, it creates this kind of plume which continues rising upward or downward in case of a dense plume, right? But there are cases, for example, here is a volcanic plume, right, which may not be getting released continuously. So it may be just one fixed volume of buoyant fluid that has got released, and now it will rise up in form of plume, right? So in this case, there is a possibility that this is the fixed volume that was released, and it has different density than the ambient fluid. It will rise up, and as it rises, it will mix with the ambient, and its volume will increase and density difference will decrease, right? So that's one example from a real plume. But then we also have some images here from a lab experiment which was performed by Scorer, and you can see this one is the reverse case. What you see here at the bottom, right? So this is a reverse case where now we are injecting denser fluid rather than lighter fluid. So in this case, a fixed volume of a dense fluid is released, and as it goes down, it mixes with the ambient, right? And it creates this kind of plume. So here is a mixing happening. As it goes further down, it mixes more, and volume continuously increases. You can see this is the volume of the plume, and what you see as a tail is just the leftover. So that's not really the plume, or the that's not the main part of the plume, but what you see as a spherical shape, that is the plume, and that is happening because of fixed volume of buoyant fluid, or dense fluid in this case, is released. Okay, and it is released just once, right? Once at a particular time. In that case, let's say it is recorded as 0 second, and after that it is stopped. Just one volume is released, and slowly that volume goes down here, and it mixes with the ambient fluid, and it increases its volume, right? And now if you inject a buoyant fluid, as you see in the upper example, it will go up, it will keep going up while mixing will continue. Okay, so this case is very different from the left one, because in the left one we don't stop the injection, we continue injection throughout the plume flow, whereas in the right hand case, we are continuously injecting, sorry, we injected or released a buoyant or dense fluid just once instead of injecting it continuously. Okay, so now let's see how it is different from the continuous injection, and what we can derive here. So let's first talk about buoyancy at the release, right? So in this case, we assume that a fixed volume, let's say, that is released. Okay, so it must have some buoyancy, as we have already studied buoyancy flux. So here it will have a buoyancy that is coming because of the density difference between the plume and the ambient. So buoyancy at the release is defined as, let's say we will call it F naught, and F naught is defined as Q naught times G prime naught. Okay, where Q naught is the volume of buoyant fluid it release, and G prime naught is the initial reduce gravity, right? And how do we define G prime naught? It will be simply rho A minus rho naught uh, divided by rho A times G. Okay, where rho is the ambient density, and here we are assuming unstratified medium, and that's why we are not really worrying about rho infinity here. Okay, which is, or I can say that this is same as rho infinity, that is the reference density. All right, and rho naught is the plume density at the release. Okay, so that is the uh, volume of the released fluid along with the G prime value. Okay, and that the delta rho that you see, rho A minus rho naught, is the early value, and as the plume rises up, rho naught, that basically is rho P, that continuously uh, increases, and that's why delta rho basically decreases with a distance, right? And now if you want to find the do the dimensional analysis, so the dimension for F naught will be, and this will give us, it is meter cube times meter per second square. So basically that gives us meter to the power 4 second square. Okay, so this is the unit for F naught. Whereas if you remember B naught that we had studied, I'll just say note, B naught was per second cube. So now you will see that F naught is actually B naught per unit time. So B naught was the buoyancy flux, where F naught is just the buoyancy. It's not per unit time, it's just the buoyancy. Okay, so that is the relation between B naught and F naught. So B naught was relevant for continuous injection because that was the rate with which buoyant fluid was released, whereas in this case we are not releasing continuously, and that's why we are just concerned about a fixed volume or fixed buoyancy of the released fluid, and that is why we define buoyancy at the source, that is F naught. All right, so now let's go ahead and try to derive the mass conservation equation and momentum conservation equation for this kind of plumes. So in this case, we are assuming that, let's say this is the solid boundary where plume was first released. If this was the original plume, after some time it goes up, it becomes like this. After further time it becomes like this, it becomes bigger and bigger, right? So that is how the plume is going up, and let's say this is at t equal to 0, this is a t1, this is a t2 which is greater than t1, this is a t3 which is greater than t2, this is a t4 that is greater than t3, etc. Okay, so at later time we are getting more and more volume. Why? Because there is entrainment happening from the ambient. So as we have seen, so there is entrainment happening continuously, right? And that is why your volume is increasing, and G prime will be decreasing. Okay, so volume conservation and volume of the plume depends on time. So let's define that as V as a function of time, and that actually increases with time. With time, right? Likewise, the reduced gravity, that is G prime, that is also a function of time, and that decreases with time. right? So because of mixing, the volume is continuously increasing, and that is why your G prime value, that is the G prime of the plume, that is decreasing, right? Where G prime here is defined as rho ambient minus rho p, where rho p is a function of time over rho ambient times G. So this is our G prime value, right? And rho p is the plume density at any time t, right? And rho p decreases with time as time increases. Right, and that is again happening because of continuous mixing. So to write volume flux balance, we use this particular equation. So let's assume that this is the plume where we have entrainment happening, right? And let's assume that entrainment is happening in normal direction, and the plume is moving upward with vertical velocity of w bar, okay? And here it has the volume v of t. Okay, so if we want to write the volume conservation equation, it will look like d v of t over dt must be equal to area over u. Okay, so u is the entrainment velocity, area a is the surface area, and v is the plume volume. So the rate of increase of plume volume must be equal to the influx of ambient fluid, right? And that is how we write the volume balance. Okay, and in this volume, as we know, is changing with time, and that must be equal to A times U. Okay, so here we define V as mr cube, where r is the plume radius, okay, and m here is a smaller than 4 by 3 is a constant, okay, that we'll find experimentally. So why we say it is 4 by 3 pi is smaller than 4 by 3 pi? Because we know that the plume that we observe here, like in this case or this case, the plume is not a perfect sphere, right? We can see it has distorted shape. It looks like a sphere, but it's not a perfect sphere, right? And that is why the volume of the plume cannot be simply defined as 4 by 3 pi r cube. And volume will be little smaller than how we usually we define the spherical volume, right? And that's why we define a must is smaller than 4 by 3 pi, and we'll try to find its value using experiment. Okay, this is happening because the plume is not a perfect sphere. All right, so that is defined, and now let's define a, that we define as a1 r square, just like the factor m we consider a factor of a1 for defining the area, right? That is the surface area of the plume. Okay, u here is proportional to w bar, as we have seen that entrainment velocity is proportional to the vertical velocity of the plume. That is something we saw in case of continuous release plume, right? And this one we will write as A to W bar. Okay, where W bar is the plume vertical velocity, okay, which is basically an average value. All right, so again A1 and A2 are constants which we will try to find experimentally. So these equations now, this equation now becomes mr cube is equal to A1 A2 r square W bar. Okay, and now what we will do, instead of considering both A1 and A2, we'll define that as a single constant. So we will assume this is equal to A, which is another constant. So this equation will become 3m r square dr by dt is equal to A r square W bar. Okay, where this cancels with this one, and the equation we get here is dr over dt is equal to A W bar by 3m. Okay, so this is our equation 1, where m and a are constants to be determined experimentally. Okay, and r is the radius of the plume and W bar is average vertical velocity. Okay, so this equation we got by balancing volume of the plume along with the entrainment volume. Now let's apply a momentum conservation on the plume. Okay, so in this case, we have to remember that we are neglecting the viscous force in case of plume. Okay, so we neglect viscous force, right? So here we will try to apply momentum conservation using the inertia force and buoyancy force. So we will assume that inertia force is balanced by the buoyancy force. Okay, so we as we keep defining this balance as rate of change of momentum must be equal to the total force exerted. So this will be Fb minus Fg. Okay, so P is the momentum, right, and Fb buoyancy force and Fg is the gravity force. Okay, now if we consider this is our plume volume, right, that is V, and let's assume that has the density of rho p, which we already considered in the last slide, right, and it has the velocity W bar. So momentum of in the plume at any point of time will simply be P will be rho p V times W bar. So that is the rho p times V will be the mass times W bar, that will be the velocity. So total will be the momentum, right, and that is the P, and what will be the Fb? Fb is the buoyancy force that is applied by the ambient fluid onto the plume. And if you remember Archimedes principle that says that buoyancy force is equal to the volume displaced, right? Force exerted by volume displaced. And that is why in this case we will consider uh, is the volume of air that is displaced or ambient is displaced, not the plume, right? And that's why we'll have to consider rho A times V times G. Okay, V is still the plume volume times G. And if G, that is the gravity force, that will be on the plume in the downward direction, right? And that will be simply rho P V times G. Okay, so these are different terms we have. So this balance can now be written as d by dt rho P V W bar is equal to rho A Vg minus rho P Vg. Okay, and now we have to consider one more factor here. So in this particular streamlines what is drawn here for the plume, you will see that while we consider this red circle as the plume, we can also see some streamlines going outside, right here, and you can see these effects, these ones, etc. So what's exactly happening is, while the buoyancy force is applied on the plume volume only, there is momentum created in the ambient fluid as well, okay, because of the buoyancy. So momentum is not just in the plume but also in the ambient fluid, and that is why this buoyancy force that is acted is not just responsible for rate of change of momentum in the plume, but that is also changing the momentum in the ambient fluid. And that is why in this balance we have to add an additional factor of 3 by 2, which again is found experimentally. This factor of 3 by 2, that is to compensate for the momentum change in the ambient fluid. Okay, so the factor of 3 by 2 here is known as the added mass effect, which is added to compensate for the momentum change in the ambient fluid. Okay, and that's why we have this factor of 3 by 2. All right, so now this equation becomes 3 by 2 rho P V W is equal to rho A minus rho P G V. Okay, and now we see that there is rho P terms in the left hand side as well as right hand side. And if you recall, few lectures back we studied an approximation called business approximation, and that says that when the density difference between a plume or gravity current or any dense fluid or buoyant fluid is not very much compared to the ambient fluid, in that case we can consider the plume density or gravity current density to be equal to the reference density, right? And that is why by applying business approximation, we can assume rho P equal to rho A, which is basically the reference density here, and that is same as the ambient density. You can assume rho P to be equal to in the left hand side, not right hand side, because right hand side has the gravity term, so we cannot change it for the right hand side, but in the left hand side we can do. So on doing this, we can actually pull rho P to the right, and this equation becomes d by dt VW bar is equal to 2 by 3 rho A minus rho P over rho A G V. Okay, and now you can figure out that this term that you have here is equal to G prime, right, which includes the G here, right. That is the definition of reduced gravity. Right, and that is why this equation becomes is equal to 2 by 3 G prime V. Okay, where G prime here is a function of time and also V here is a function of time. So both the reduced gravity and the volume are function of time. But we have to remember that G prime T times V of T, that is actually the buoyancy. Okay, that is the buoyancy of the plume. But because the ambient is unstratified, which means rho is constant, F remains constant despite the entrainment. Therefore, F is actually not a function of time, but F is simply equal to F naught. Okay, so what's happening here is we know that G prime times V is equal to buoyancy, and in case of unstratified medium, as we have seen for continuous release case, that if the medium is unstratified, buoyancy of the plume does not change. So ambient does not affect the buoyancy and buoyancy remains constant even if there is entrainment into the plume. And that is exactly what's happening here. There is entrainment happening, there is mixing happening, and that is why the volume increases and G prime decreases, but both of them happen at the same rate. One increases with the rate of decrease of the other, and that is why this remains constant. So F is not a function of time, it is just a constant, and that is equal to the source buoyancy. Okay, which is basically the source buoyancy. All right, and that is why this equation that we have above can be written as VW bar over dt is equal to 2 by 3 F naught, where that is a constant now, right? And this equation now if we multiply or integrate this basically will give us VW bar is equal to 2 by 3 F naught times T plus, let's say, C1. C1 is a constant, constant of integration, but we assume V is equal to 0 at T equal to 0, so that gives us C1 equal to 0. Okay, this is for an ideal case. For an ideal case, and that is why the above equation can be simply written as 2 by 3 F naught T, or W bar can be written as 2 by 3 F naught T over V. Okay, this is our equation number 2 that we got using volume flux balance. And now if you're wondering about this particular criteria, what we have done here, that is when in case of an ideal plume, we assume that the plume is generated only because of buoyancy. And now you may argue that buoyancy is coming from volume and G prime. So we assume that volume is 0 at the injection, and G prime is infinity. So that actually makes buoyancy as a finite value with zero volume and infinity G prime. So that's again for an ideal case. In reality, it may not be true, and we'll have to make some adjustment. But in assuming this ideal case, we can consider C1 to be equal to zero. Okay, and that gives us this equation number 2 from volume flux.